How to do that? Let us see. So if I see this particular number, so I have taken couple of examples. So where some of these numbers are positive, some of these numbers are large, some of these numbers are small. So if I have these numbers, now what I see couple of interesting things. One thing that if I can specify, I can say that out of my n number of bits, let's say out of my 16 bits or out of my 32 bit, I assign couple of bits for this part and some bits for this part. That would be good, and maybe some bits for plus and minus. Okay, so before doing that, let's try to understand how to read these numbers. So one thing we call, this particular thing we call significant. Significant would be 1 point and then these numbers. So this is called significant, and in the significant, because of our normal definition, in the definition of our normal scientific notations, we said this a number before decimal point has to be non-zero. So in this case, in case of decimal exponential numbers, it could be 1, 2, 3, 4, 5, 6, 7, 8, 9. But because it is binary, we have only one choice. It can be only 1. Okay, and the way we define significant is actually this digit dot rest of the digits. They're called significants. Now the significant could be plus, could be positive number, could be a negative number. So this is one particular thing. And now because in a normal notation, this before the decimal point, it is going to be 1. So I can also define one more part, which is a fractional part, which is also called mantissa. So this fractional part could have zeros, it could have combination of zeros and ones. So this is called mantissa. And the third thing is exponent. In exponent also, I can assume that because it's a binary number, it is always going to be the power of 2. Now there is another number, 2's power what? So this 2's power is the exponent value. Again, this exponent value could be positive, could be negative. Essentially, if I combine all of these things, then I can, out of let's say my 16 bit or 32 bits, I can choose 1 bit for the sign of significant, whether significant is positive or negative, and then few bits I can choose, I can fix for exponent, and rest of the bits I can choose for the mantissa. So I need not to represent decimal point, but again decimal point would be implicit here. Similarly, this 2 or this multiplication sign is also implicit in nature. What we have done is that out of this whole this notations, this exponential notations or normal notations for binary numbers, normal exponent notations for binary numbers, we see that this is a 3 piece of information. If we are able to store, that means we can regenerate or calculate what was that floating point number. One, I need to know whether that number is a positive number or a negative number. The second thing, what is the value of mantissa? See, we are not talking about significant, because in significant, this 1 bit, because in a normal form, this is always going to be 1. So we can again, this we can take it as a implicit information. Okay, so we are taking the mantissa part, and we only know the exponential values. So if we know the exponent values, we know the mantissa, and we know the sign bit, then we can reconstruct this floating point number or a real number. Okay, so the question now which arises here, that how many bits should we assign for exponent, how many bits should we assign for Mentissa? Sign would definitely require only one bit. We can say 0 means positive, 1 means negative. So one bit is sufficient to represent sign. But for exponent and Mentissa, this is always a question that how many bits would be required. And again, for the sake of for information, I can tell you that when these floating point numbers were initially invented, or this particular way was converged that this is how we'll represent floating point numbers, every manufacturer, people who were designing their calculators or their computers, they were choosing their own number of exponent bits and Mentissa bits. So it was not standardized, and the problem was faced when two different vendors were communicating the information. So let's say vendor 1 was writing all the information in magnetic tape, the other vendor want to read it. Now how will they know that what was their format? So there comes the standardization. Now in case of computer science and electrical engineering, standardization is done by IEEE. IEEE is a society. It's called Institute of Electrical and Electronics Engineers. So it's a institute, or it's a society which does a lot of things. It publishes papers, it publishes books, and it also help us in increasing our knowledge base in electrical and electronics. Computer science is also considered a sub portion of electrical and electronics when we see it in a wholesome manner. So they also take care of this additional thing that wherever standardization is required, wherever people have different views, they will create a standard procedure, they will create a standard definitions. So similarly, when they observe that floating point representation have different representation floating around, every vendor is creating their own representation. So they said that okay, there is only one standard, everybody is going to follow this particular one, and all these standards are given some name. So this IEEE standard is given IEEE 754 as the standard name. So in this standard name, we are going to use this by default. If it is not said, then we will by default use this IEEE 754 floating point standard. So let's say the number is 32-bit. In 32-bit number, 1 bit would be used for sign and 8 bits are used for exponent. Now, as we have seen in our previous slide, this exponent could be positive, exponent could be negative. So we need to have some representation of negative numbers here. So if we remember in our previous classes, we have seen that my sign number could be represented either using sign magnitude or using 1's complement, 2's complement, or bias method. Here they have picked bias method for representing exponent. Why they have used bias method for representing exponent? Because here we are not supposed to do multiplication, mostly it is addition and subtraction, so that is why a bias method is sufficient and good. And bias of 127, and we right now for a couple of slides we just assume that 0 and 255 are not used. So the range of numbers which can be represented in exponent is from 1 to 254. They are all valid. Other than 1 and 254, nothing is valid. They are not valid, and they are used for some special purpose which we will see later in the lecture, or maybe in the next lecture. Rest of the bits, 23 bits for Mentissa. So you will also see these numbers are essentially they are using sign magnitude form, because we have one bit which is used only to represent sign. So here 2's complement method of representing negative numbers are used in integers, but rest of the two methods like sign magnitude, because we are representing one bit as a sign, and also bias method of representing negative number is used in this floating point notation. Okay, so if we have these three piece of information, I'm calling it S, E and M, then I can construct my final number as minus 1 into S or minus 1 is to power S. Actually it should be minus 1 power S multiplied by 1 plus 0 point m into 2 is to power e. So if I have this 32-bit number from 0 bit to 22 bit, essentially total of 23 bits would be used for Mantissa, and the bit number 23 to bit number 30 would be used for exponent, and 31st bit would be used for sign. Why this particular way of representing? So it has certain advantage that, like our integers, my MSB here is telling me whether the number is positive or negative. So I can use the same method to find out whether the number is positive or negative. Means last bit I can check, and there is no particular way why Mantissa and exponents are given these particular set of bits, but because exponent is given MSB and Mantissa is given lower side or basically lower significant bits, so that there is no particular reason for this thing, but this is how it is organized. And because it is given in a standard, so we can always follow that this particular way or this particular bit would represent Mantissa or exponent, etc. Okay, so now this is probably not clear unless we take some examples that how a number would be represented and how Mantissa or how exponent would be calculated. So let us see with some examples that how do we compute or how do we see a floating point number. So to take this example, to have this understanding, let's take a decimal number as 24.25. So this 24.25 I want to represent in binary, so I said it is these are all power of 2's. So 16 plus 8 is 24, and then 1 by 4 is 0.25. 1 by 4 is 2 to the power minus 2. So that means I can represent this number in a binary way. I can write it like 1 1 0 0 0, and then there is a decimal point, then 0 1. Now then I will have to write this binary number in a normal scientific form. In a normal scientific form, there would be only one significant digit. So significant digit means non-zero digit before this decimal point, and after that rest of the digits would be there. So if I want to write in this form, then I need to calculate how many what is the 2's power, what is the exponent value. So 1 2 3 4. So that means I can write this whole number as 1 point. I can push this decimal point at this place, 1.100001, and 2 is to the power 4. So once we have constructed this normal scientific form, after constructing this normal scientific form, then I can segregate or I can find out the three values which I require. I require sign bit, Mantissa and exponent. So because this number is a positive number, then we write sign bit as 0. Mantissa means this significant digit we remove, and after removing significant digit, whatever is left is a fractional part or Mantissa parts that we write here. So we are writing all the 23 bits in this fashion. Now I'll give you here one trick, that because the number of bits are 23 and finally we have to find out a number which is 32 bit in nature, so it would be always better to write this number in a hexadecimal form, so we'll have only 8 digits. Okay, so because it is 23 bits, what I'm doing is I'm grouping them in the groups of first first 3 bits, and after that the group of 4 bits. So I'll have 5 groups of 4 bits, and so essentially I have 5 nibbles here and one group of 3 bits. So this is the mantissa. Now exponent, we said there is a base of 127, so that means whatever exponent we are getting after this normal form, we have to add 127s, we have to add this bias. So after adding this bias, it will become 127 plus 4, that means 131. And now this, if I want to represent 131 in 8 bits, then it will become 1000001. So again, you see I have made the grouping like this: first 3 bits, then 4 bits, then 1 bit. Why I am doing so, you will see later. So now I would like to construct my floating point number, and what I will do is I'll put my sign bit at 31st place, and then exponent bits, and then mantissa bits. So because 31st bit is a sign bit, then I would require 3 another bits from the exponent to complete this nibble. That's why the group of 3, 4 and 1 was constructed. Then a next nibble from the exponent can be written here. Then the next bit, last bit of the exponent would be written here, and then I can write mantissa. So first 3 bits of mantissa, and then rest 5 nibbles of the mantissa. Now all these are now written in 8 different nibbles. From these 8 different nibbles, now I can construct my hexadecimal number, which is a quick and which is 1-to-1 representation corresponding to binary numbers. So it is 0 cross 4 1 C 2 0 0 0 0. So this is how we can represent, or we can convert any number into a floating point number. So let's take some more example. Let's say the number is 0.625. I'm taking easier examples. I'm leaving the hard examples for the tutorial session and for your exams. Yeah, this is a joke. So let's see. So we'll try to see, at least cover a couple of examples here, and we can see during the exams that how do we go. So this 0.625 can also be written like a 0.5, that means 1/2, and 0.125, that means 1/8. In other words, if I want to write this in binary, then it would be 0.101. And making this particular number in a normal scientific form, it would require 1.01, because the first significant digit is 1, so that means it has to be pushed like this, and 1.01 into 2 to the power minus 1. So we have now all the information. We know the number is positive, we know what is mantissa 0, 1, and we also know what is exponent. Now we can construct a floating point number. So in a floating point number, sign would be 0, and mantissa is 0, 1, 0, and rest for all the nibbles it's going to be 0. And exponent, because we have a bias of 127, so we'll add -1 to 127, so that means it will become 126, and then we can convert this 126 into binary, that means 0, 1, 1, 1, 1, 1, 1 and 0. You can ask me, how do I do it so quickly? It's not only because I have pre-calculated, but because 127 means all 7 ones. It is 1 less than 128, that means 7 ones would mean 127, and now I am subtracting 1, so that means the last bit will become 0. So this is the trick to calculate a binary numbers quickly without going through that divide by 2 procedure. So now I have all the information. I can club that information to create my floating point number. So sign I will keep here at 0, and then these 3 bits of exponent, and then these 4 bits of exponent, then last bit of exponent, and then my mantissa of 0, 1, 0, and then rest nibbles of zeros. So I can construct this. This will become 0 cross 3 F, and this is 2 and then 5 zeros. So this is the hexadecimal representation of this number 0.625. Let's take some example of a negative number. The example is very similar to previous one, so I can go little fast. So because it is 2 is already a power of 2, so I can write it as 10.101, and then this number in a normal scientific way would be written as 1. Basically decimal has shifted towards left, 1 point it has shifted, so that means 2 to the power 1 will become as the exponent factor. Now with the normal scientific, after creating my normal scientific form, I know the all the exponent, mantissa as well as sign bit. So yeah, sorry, here sign bit has to be a negative here. So now sign bit, because it was a negative, so I am putting sign as 1, and mantissa is these 4 bits. 0 1 0 I'll put in first place, and then after that 1, and then the rest of the zeros I'll keep the trailing zeros, and rest of the bits are also 0. For the exponent, 1 would be added to 127 because 127 was the base address, or basically the offset. So this offset or bias, so in the bias we add 1, it becomes 128. 128 means 1 followed by 7 zeros. Then we can again combine these 3 factors, sign, mantissa and exponent, to create our floating point number in a hexadecimal way. One more example which looks quite simple, but it is important to touch that also. Let's say I want to represent 1. Now you see there is no decimal, but because I want to represent 1 in a floating point notation, I have to write it like 1.0 into 2 to the power 0. Okay, so here my mantissa is 0, my exponent is also 0, my sign is also 0. How do I represent this number? For mantissa, it is going to be all bits will be 0, all 23 bits will be 0, sign would be 0, and exponent in 127 0 would be added. That means it will be 127 only, 0 and then 7 ones. Then I can combine all of these, and then the resultant floating point number in hexadecimal is 0 cross 3 F 8 5 zeros. So this also give us one food of thought, that whenever we are converting any decimal number, and so whenever you are writing C++ code or Java code, and you are simply writing you want to typecast an integer to float, you want to say that this integer should be converted into a float number, then all of this processing step would happen. And let us say number was written as 1 there, but in a floating point notation it won't be written as 1. It's a more sophisticated form. It also requires a lot of steps to convert an integer to a floating point number. Now one can again ask that why do I want to convert an integer into a floating point number? Again, my answer is very similar to the examples we have taken for large numbers. So let's say the number has some 20 digits, 20 decimal digits. If number has some 20 decimal digits, so that means I need to convert those 20 decimal digits into binary digits, which would be probably more than 60 or 70. Now, because I have to represent them, but again the lower significant digits may not be useful for all practical purposes, so if I make that as a floating point number, that can help me in easing of certain operations. So whenever a large integers need to be represented, then those integers are also represented using a floating point number. So with this, I would like to close this lecture, and in summary, what we have learned in this lecture is that we learned that how real numbers can be represented in a binary form, and how decimal point would be represented, how exponent would be represented. So we finally observed that there are two ways of representing a real number. Either we put it in a fixed point format or we put it in a floating point format. Fixed point format gives us certain advantage that it is easy to operate with. We can use integer operations of addition, subtraction, multiplication, but it severely limit the amount of precision and range. On the other hand, floating point notation is a complex operation in conversion itself. We have to identify what is mantissa, we have to identify what is sign, we have to identify what is exponent, and then add the bias in the exponent, and then construct a floating point number. So this is all for today. Thank you very much. Good luck.